Hey
My
everyone, and welcome back to the podcast. Today we're diving deep into a question that's becoming increasingly important in our AI driven world. How can we truly trust machine learning systems, especially when they're so complex that even their creators don't fully understand how they work? Honestly, it's a genuine problem, especially considering how rapidly these artificial intelligence solutions are getting integrated into our daily lives. Even AI scientists like researchers such as Sam Bowman, who have spent years working on language models like ChatGPT, by the way, don't really understand what's happening inside these models. Bowman describes it in a Vox interview as seeing millions of numbers flipping around hundreds of times a second. It's really hard to make sense of all this noise under the hood as a human.
exactly. The black box nature of machine learning models is a real head scratcher. You have got your inputs, you know the general architecture of the model, but predicting the exact output for a given input, forget about it. It's like trying to guess what a magician is going to pull out of a hat. Except the hat is filled with millions of interconnected, constantly shifting parameters.
Right. And it's not just that they're complex. Yeah, they are, but there's more to it than that. It's that they learn in a fundamentally different way than traditional software. We're talking about inductive learning. Machine learning models don't follow pre-programmed rules. They have to sift through mountains of data, then identify patterns on that data, and then encode those patterns into their internal parameters. Yeah, it's a powerful technique, but it also means that their decision making process is opaque, like a solid black box. We are simply unable to look inside and derive meaningful insights.
And to make things even more interesting, we have to remember that machine learning models are inherently statistical. Their outputs are probabilities, not certainties. There is never anything set in stone 100%. They make predictions based on a statistical inference, which means there is always a chance they will be wrong.
Yeah, that's a great point. And unlike traditional software, where you can often pinpoint a bug to a specific line of code and send the dev team in to fix it, with machine learning, there's no rule book to rewrite. Tweaking the model is more like adjusting a web of interconnected probabilities rather than making a simple code change. It is a very delicate, time consuming, and resource intensive process.
Sounds like trying to fix a leaky faucet by adjusting the entire city's water pressure. And that's not even mentioning the complexity of the input data itself. Think about tasks like image recognition or natural language processing. The relationships between inputs and outputs are so nonlinear and intricate that isolating the impact of a single pixel or word is practically impossible.
Exactly. So, if traditional testing methods rely on understanding a system's internal logic, how on earth do we test these black box models effectively?
That's the $1 million question. So, in this paper we have been reviewing, there was something mentioned called probabilistically extended ontologies or POs. At this, that sounds intriguing. Uh, can you tell us more about it?
Sure. Peons are a novel concept introduced in this paper that we were talking about that offers a framework for testing machine learning systems without needing to crack open the black box. We don't need to know the system's internal logic in order to see if the system is performing effectively.
Okay, I'm hooked. But before we get to peons, maybe we should quickly explain what regular ontologies are for our listeners who might not be familiar.
That's a good idea, and I'll do just that. So you can think of ontologies as these detailed formal knowledge maps for a specific domain. They can consist of 3 different categories of things. 1 are classes, 2 are properties, and 3 are relationships. So for classes, you can think of them as core entities or concepts. So if we're talking about a self-driving car scenario as our machine learning problem, then classes involved in this could be the person class, the vehicle class, the road class, or even the traffic light class. Okay, moving on to the second thing, properties. Properties are just attributes or characteristics of the classes we earlier discussed. So if we take the class person might have attributes or properties like age, height, activity, what they're doing. Vehicle might have properties like the type of vehicle, the speed, the color, and these types of things. And relationships, the third category of things, are things that define how entities are connected. So for example, a person can cross a road. These are 2 entities interacting with each other. Or a vehicle drives on a road, or a person drives a vehicle, or a traffic light controls the flow of vehicles. So this is what the basics are for ontologies.
Okay, I see. So a structured way to represent knowledge about a specific area. Now, how do we get from regular ontologies to these probabilistically extended ones? I mean, the peons.
Yeah, so peons take the ontologies to the next level, another step further, by incorporating probability distributions, as the name suggests. So let's stick with the self-driving car example. Imagine the ontology defines partitions of the input data like this. So if you have pedestrians, okay, child, adult, elderly. You have vehicles, so you can have cars, trucks, bikes. You have weather conditions, sunny, rainy, snowy. You have time of day, daytime, nighttime, whatever. A peon would then assign probabilities to these partitions based on how likely they are to occur in the real world. This is important. So for instance, you could have an adult walking in the daytime on a sunny day. This is a high probability of happening in real life. Something that's a low probability of happening in real life is a child on a bike in snowy weather at night.
I see. So it's not just about organizing the information, it's about reflecting how often different situations actually happen in the real world, isn't it?
Mm-hmm. Yep, that's correct. This is what the authors of the paper I'm talking about call representative testing. So by incorporating these probabilities, we can test machine learning models in a way that actually mirrors real-world distributions of scenarios, which will be encountered by the model, or the self-driving car model in this case. We could even use other examples for this technique that are not mentioned in the paper, such as creating spam filters. So we can use peons to make a spam filter that would include classes like the email sender. Okay, is this person sending the email a known spammer, or are they a legitimate contact? We can have another class called email content. So what's actually in the message content? Are there links in there? Are there uses of urgent language like please buy now or redeem immediately? And then we can also see other things like attachment type. So what kinds of files are being sent in the emails? Are there PDFs? Are there .exe files, text files? What's going on? The probabilities would reflect the likelihood of different types of spam and legitimate email, and that would be the thing that tests if the spam filter is actually working as intended. We could also have something for e-commerce. We can also have something for music or movie recommendations. The list goes on and on. The possibilities with peons for evaluation are endless.
That makes sense. But how does having these probabilities help us define when we are done testing? It seems like you could test forever.
Yeah, and that's where the statistical aspect comes in. We just need to be statistically significant result. Peons, combined with an adaptation of something called the uniformity hypothesis, allow us to calculate statistically significant sample sizes for our tests. And this gives us a clear, objective end of test criteria. At that point, we can say we've tested enough when we're X% confident that the system meets our quality requirements. We don't need to be 100% confident. Even 95 or 96 can cut it depending on the use case.
That's powerful. It moves us from ad hoc testing to something much more rigorous. And you mentioned the uniformity hypothesis. What's that about?
Okay, so in traditional software testing and deductive based approaches, the uniformity hypothesis basically says that if a test passes for one value within a certain range, then it should also pass for all of the values in that range. Now, the authors of the paper I'm talking about adapt this approach for machine learning as well. The probability of a test failing should be roughly the same for all of the inputs in a specific partition of our ontology. That's what the uniformity hypothesis is about.
Okay. So if our partition is a pedestrian child, weather rainy, then any image of a child in rainy weather should have a similar chance of being misclassified by the self-driving cars pedestrian detection systems.
Yep, precisely. And if we find that the failure probability varies a lot within a partition, because maybe it's not detecting taller children as children, or maybe it's not detecting female children as children, or it's not detecting black children as children, then that's a signal that we need to refine our ontology further, maybe by adding more properties or creating fine-grained partitions, like adding a gender component to it, adding a race component to it, adding a height component to it, and so on.
That makes sense. It's like a feedback loop that helps us improve both our testing and our understanding of the system's limitations. Earlier, you touched upon ethical considerations as well. How do peons play into that?
Yeah, so this is also another crucial aspect. Peons allow us to explicitly address fairness and bias. So, for example, if we're testing a facial recognition system or even the pedestrian object detection system, we can use the peon to ensure that we have a uniform distribution of test cases across different skin tones or genders, so that we don't go into those earlier problems of misclassification. And this helps us identify and mitigate potential biases in our systems.
That's the game changer for ethical AI development. Now, let's step back a bit. How does this whole peons-based approach compare to how we traditionally test software?
So traditional software relies on deductive reasoning. You've got a set of rules, and you test whether the software follows those rules correctly. You might use techniques like n-wise testing to check different combinations of inputs, but that's about it. For ML systems, they're fundamentally different. Machine learning systems learn inductively from data, and so their behavior is probabilistic.
So traditional testing methods are like checking if a meticulously crafted clock is keeping time accurately, while machine learning testing is like trying to predict the behavior of a flock of birds. You know the general tendencies, but individual actions are unpredictable.
Yeah, that's a great analogy. The paper actually demonstrates how n-wise testing, which is a common traditional method, fails. It falls short when it's applied to machine learning systems to evaluate them. They actually did an experiment with an object detection system in the paper, and n-wise testing just could not reproduce the system's key quality criteria or align with the development process. So in other words, it just could not meet the expectations.
That's a clear illustration of the limitations. So, what about testing methods that are specifically designed for machine learning? How do they compare?
Well, machine learning based testing methods bring a lot to the table. They're equipped to handle the sheer complexity and scale of modern machine learning systems. They can analyze massive amounts of data and then generate a wide, diverse range of test cases on that data, which would be almost impossible to do manually, or at least very expensive.
That's a huge advantage in terms of efficiency.
Absolutely. And on top of this, these systems are also adaptable. As the machine learning systems evolve and learn, the testing methods can also adjust to keep up with the pace. They are highly automatable, which means that we can run tests more frequently, more comprehensively, and with less manual effort.
That sounds like a win-win-win. What about areas where traditional methods really struggle, like ensuring fairness or detecting subtle biases that might be hidden deep within the model?
This is where machine learning based testing really shines because these methods can analyze the system's outputs across a vast range of inputs. They're really excellent at uncovering hidden biases or revealing inconsistencies that may actually not be apparent from just looking at overall partition metrics. So when we analyze a machine learning model's performance across different scenarios, it'll help us spot hidden biases that might not show up in overall results. So for example, if the model detects cyclists well during the day, but then struggles to identify them at night, this could reveal a bias in how the model handles low light conditions, which could potentially lead to some serious damage. So we also look for unexpected behavior like the model being inconsistent in certain situations, even if it is generally accurate overall. So by breaking down performance across these partitions, we can then uncover issues and improve the model's reliability in all kinds of real-world conditions. This is what machine learning models do, and it can even extend testing to cover non-functional requirements, things like robustness, fairness, explainability, which are often difficult to assess with traditional methods.
And it sounds like this could be a solution to the Oracle problem too. In traditional testing, you often need a precise definition of the expected output for each input, which is just not feasible for many machine learning systems.
Exactly. Instead of relying on a perfect, all-knowing, all-seeing oracle, machine learning-based testing focuses on the statistical behavior of the system. It looks for deviations from expected patterns to come to conclusions. And that's what the peons do, for example.
This is truly fascinating. It feels like peons and machine learning based testing are fundamentally changing the way we approach the evaluation of these complex systems.
Yeah, they really are. And the paper emphasizes the ethical dimensions too. So by using peons, we can proactively work to ensure fairness and to prevent bias in our machine learning systems. The authors of the paper are even looking ahead to developing tools that will make it easier to create these ontologies and to use them to analyze weaknesses in machine learning systems that currently exist.
Wow. It sounds like the future of testing is just as innovative and complex as the AI systems it's designed to validate.
Yeah, I couldn't agree more. With frameworks like Peons, we are moving closer and closer to a world where we can build machine learning systems that are not only powerful and effective, but also trustworthy, ethical, and reliable. That's all for our podcast. Thank you for tuning in.